Hi, this is Barrett Gibbons, and in this video, we're going to define a new concept, the concept of limit points, and then we'll see a couple of examples in the standard topology on R. Okay, so the concept we're defining is limit points. So we take a topological space X and take a point A somewhere in X and a subset A, a subset of X, and we say that little a is a limit point of capital A if and only if every open set U that contains A, little a, has to intersect capital A in at least one point other than little a. So let's go ahead and draw a Venn diagram to build a little bit of intuition about what this looks like. So I have a set capital A and a point little a. I have a set capital A and a point little a. So maybe little a is a point, and then capital A, I'm kind of going to try to draw capital A sort of near little a, but little a might be in capital A or it might not. Okay, could be either one. And then we say that every open set U containing A, so any neighborhood in a way that I draw of little a, so any open set containing A, that's my U, has to contain at least one point other than little a. So there has to be some other point of capital A other than little a. So maybe there's like a B right there. Okay. So little a might be in capital A, but like that wouldn't count. Okay. So, all right. And then sometimes the set of limit points is denoted by A prime. So we often will write A prime. That's not standard, but I've seen that in many different topology textbooks. And so it is a pretty common one. But if you're going to use that notation in the future, you'd always want to clarify and say, like, by A prime, I mean the set of limit points. Okay, so in some ways, the idea of a limit point, it's kind of saying that little a is like close to capital A in the sense that no matter how small of an open set you draw containing little a, that open set has to touch capital A. All right, let's see some examples in the standard topology on the reals. So, okay, let's let X be the standard topology on the reals, and let's find the limit points of each of these three sets. So we'll start with this one over here. The interval that from 0 to 1, excluding 0, but including 1, and then the point 2. And remember that in this topology, the basic open sets are the open intervals. So this looks like 0, 1, 2, and everything in between here. Okay, and limit points might be inside your set or they might be outside your set. So we have to kind of think about all different kinds of points here. Just to make it a little bit easier to talk about, let's go ahead and just name this set A. So we'll call it A. Okay, so that's the set A right there. All right, so we have to think about the different types of points. So let's start by thinking about what about a point that's less than 0? If I take a point that's less than 0, I want to think about all possible open intervals. Does every open interval, if I take a point down here, does every open interval around that point have to touch A? No, I can make some open intervals that are small enough around points down there that it stays away from A. So that's not a limit point down there. Okay, what about 0 itself? What about 0 itself? If I draw an open interval around 0, will it have to touch points of capital A? Yes, it will, because if I draw an open interval around 0, then the upper bound of that interval will be a positive number. It'll be a little bit to the right, and there's points of A to the right of 0. You'd have to touch some points of A in this region. Okay, so 0 is a limit point. What about points between 0 and 1? If I take a random point between 0 and 1 and I look at an open interval about it, will that open interval have points of A other than the one that I started with? Yeah, it'll have a lot of points of A, right? So all the points inside that interval are limit points. What about 1, the other endpoint? If I draw an open interval around 1, will it have to touch points of A other than 1? 1 we already know is in the interval, but other than 1. Yeah, because the open interval that contains 1 will have some numbers below 1, and those numbers are all in A. Okay, between 1 and 2, I think we can believe that I can draw an open interval that avoids A, and so therefore that's not a limit point. Now, what about 2 itself? Can I draw an open interval around 2? Does that open interval intersect with A? Well, it does because 2 is in the interval and 2 is also in A. But does it intersect with A in a point other than 2? No. So part of the definition of a limit point is that you must intersect with the set you're looking at in at least one point other than the particular point that you're looking at. So this other than A part right here, when I look at the number 2 over here and I draw a little interval around it, maybe I draw the interval that goes from 1.5 to 2.5. That's an interval U. It's an open set that doesn't contain any points of A other than 2. So 2 is not a limit point. Okay, so the limit points in this case are, okay, nothing less than 0, 0 to 1, everything in between there is included, and then the endpoints, 0 to 1, are included, but 2 is not a limit point. So the limit points of this capital A consist of all the points in the closed interval from 0 to 1. Okay? All right, let's do another example. Let's find the limit points of the set of all numbers of the form n plus 1 over n, where n is a natural number. And again, just to build some intuition, let's just list out the first few of these. So like when n is 1, we get 2. I was going to write 2 over 1, but I can do some arithmetic. 2 over 1 is 2. When n is 2, I get 3/2. When n is 3, I get 4/3. I'm having a technical difficulty. There it is. My Apple Pencil's at 0. Okay, when n is 3, I get 4/3. When n is 4, I get 5/4. So it looks like 2, 3/2, 4/3, 5/4, 6/5, and so on and so on and so on. So just intuitively, from an analysis class or even from a calculus class, what do you think the limit of that sequence is as n goes to infinity? What is the limit of that sequence as n goes to infinity? You might also want to write them as decimals: 1, 1.5, 1.33, 1.25, 1.20. They're getting smaller as you go. They're getting smaller as you go. What are they getting closer and closer to? It looks to me like they're getting closer and closer to the number 1. Okay. And I could also use analysis facts. I could say, yeah, that limit, I know how to compute that from calculus, actually. The limit of those, if that were a sequence, the limit would be 1. Okay. I can also draw it on a number line. So I've got, 2 here, 1 here. So it's 2, 3/2, 4/3, 5/4, 6/5, 7/6, and so on. Okay. So now let's ask which of these are limit points of the set. Well, I think it's pretty clear that anything kind of other than 1 or 2 or any of these other special points, like if I take a point, here or down here or something like away from the other points, I can always draw small enough little intervals around those points that won't touch anything. So none of those are limit points. What about these points themselves? Like, well, what about, for example, like 4/3? If I were to look at 4/3, can I draw an interval around 4/3 that is small enough that it doesn't touch any of the guys on either side of it? Yeah, I mean they're close together, but they don't touch, so I can squeeze a little interval in. So 4/3 is not a limit point. What about, 5/4? No, for the same reason, I can always put a little interval around it that doesn't touch the other ones. I mean, my drawing makes it hard to do, but I can do it. So none of the actual points of this set are limit points. Okay, but now what about the number one? What about the number one? So if I look at the number one and I draw a little open interval around one, well, as the points of this set continue to, as I go sort of to larger and larger n, these values get closer and closer and closer to one, right? And they approach one, they get infinitely close to one. They get arbitrarily close to one, you might say. And so whatever interval I draw, there's going to be some of these points that are inside of that interval. And so one is a limit point. And so for this particular set, let's call this set B. The set of limit points of B is just the point 1. Okay. And now let's think about the limit points of the set of rationals, the limit points of the set of rationals in the standard topology on R. So I can think about two different kinds of points here, right? I might want to think about each rational point, and then I want to think about each irrational point. So I'm going to think about each of those types of points and try to figure out whether each type of point is a limit point of the rationals. And again, I'm going to draw a number line. Make it a little bigger, I guess. And then I'll draw the rationals as sort of blue points. I'm just going to make a whole bunch of dots. I'm trying to just picture the fact that these dots are just everywhere, all over the real line. And then I'll make the irrationals into these purple points, and they're sort of fully mixed in. Okay, so now consider a rational number, P. If I look at an open interval, if P is in an open interval, A comma B, will that A comma B also touch Q in points other than P? So take a point P right here. Look at this open interval around it. Will there be some rational numbers inside that interval? Yes, every interval has infinitely many rational numbers in it. Okay. What if I take a point that is irrational? If Q is in some interval, here's my irrational Q, and I take an interval around it, will that also contain more rationals? Yeah, for the same reason. Actually, every interval contains infinitely many rational numbers. So no matter what kind of point you start with, actually, if you take an open set containing that point, it will intersect with the rationals in points other than the point itself. And so what that says is that everything is a limit point of Q. Everything is a limit point of Q. So the collection of limit points of Q is all reals. Okay, so that is 3 examples in the standard topology of a limit point. So the definition of a limit point is take point A and take a subset, take a point little a, take a subset capital A. We say little a is a limit point of capital A if and only if every open set containing A intersects capital A in at least one point other than little a. And we found the limit points. So we saw that in the standard topology, first of all, if you look at the first example, one of the ideas you can get from there is if you have a point that's isolated, like 2 is kind of like by itself, it doesn't have other points like around it. In the standard topology, that kind of a point will not be a limit point of your set. Okay. But when you have an interval, everything inside of the interval, along with the endpoints, will be limit points in the standard topology. Example B kind of shows you the same thing because each of those points, 2, 3 halves, 4 thirds, each of those is sort of isolated in the sense that there's You can put intervals around them where they're the only one in that from the set in that interval. But the point one is a limit point, and kind of intuitively, it's because that sequence approaches one in a calculus sense. And then finally, the rational numbers, all real numbers are limit points of the rational numbers. And that's kind of a way of saying that in the standard topology, the rationals are sort of evenly scattered all over everywhere. Like they're sort of every real number has rational numbers arbitrarily close to them. Okay. So that's the definition of limit points and some of the intuition that we get by kind of investigating what limit points are in the standard topology. Thank you for listening.